We are a team of UCL students, and this is our ImagineCup competition submission. At its core, this is a project to visualize big data, and we are creating the API that can be used by front-end developers to acquire the data for their visualizations. The database generator is a tool we created to help us populate a dummy database to use for our experiments in our project. It creates a dummy school database schema with schools, students, teachers, and several statistics like attendance, grades, etc. In the structure folder, we can see the database schema, and these files are executed to create the entity relationships in the database. In the SQL files folder, there are generated SQL queries created from the database generator tool, and this is used to create the data on the dummy database. This is the entity relationship diagram of the database created by the database generation tool. We will now go through each component of our system from a high-level perspective. The set engine reads from a database. In our experiments, this was a school database, and then it creates the sets from the database in a set creation process. This will be demonstrated later on in the video. The set engine uses a blob writer to write the sets onto the Azure Blob service where they are stored. We decided to use a REST service to give access to the data to front-end developers. Using this web API, developers can request different types of sets as seen in the diagram. We have created additional endpoints specifically for retrieving chart-ready data. These chart objects are created by the chart engine because it can be much simpler to generate these charts in the backend than in the front end. The chart engine reads from the blob to get the necessary data. The set engine is a general-purpose tool that we created to generate sets of data from any given database. It can traverse the structure of any database and create these sets of data without any prior knowledge of set structure. We are going to demonstrate a run of the set engine against our dummy database. In practice, this would run on a Windows task scheduler on a weekly basis to ensure that sets are up to date. Here we can see the set engine going through each table and trying to create sets and subsets as best as it can. The set engine takes about 10 minutes to execute on a normal database, so we're going to fast forward to the end. Here is the end of the set engine run, and we can see that it has successfully finished executing. At the end of every run of the set engine, results can be automatically emailed to the system administrator so they are notified whether anything has gone wrong. One of the ways to store the generated sets that we experimented with was by using an Azure Blob storage solution. We can now see the output of the set engine on the blob. The set engine creates a map of the blob in a file called setMap. The set engine has created and organized the sets. In this sample set space, we can see parent sets such as city, region, and population. If we go into the city folder, we can see that the set engine has categorized the data into individual cities. Notice that sets have a size tag, which returns the size of the set. Similarly, if we go into the population folder, we can see that the set engine has categorized this data into percentiles. And if we go into the public folder, then we can see that the set engine has managed to categorize Boolean data, 0 meaning the school is public and 1 meaning the school is private. In order for the front-end developers to access the functionalities we have developed, we have created a web API which is hosted on Microsoft Azure. We try to keep the URLs of our API uniform by adhering to the common practice of using singular nouns to suffix our requests. We found that we were driven to increasing the depth of our URLs in a way which made the API unnecessarily complex. To combat this, we changed our structure early on and we adopted the question mark parameterization format. Here we can see an example of the API request and response to the chart engine, which in this example returns dummy data concerning students and the number of A's they achieved. This data is formatted in a way which can be immediately plotted to a graph without much further calculation. In this example, a set of student GUIDs along with a single property, their gender, is returned as JSON. This example is a little bit more involved. Here we can see that we are requesting a set of a particular type, student, to be accompanied by a specific property, again their gender. Furthermore, we are providing a filter parameter which instructs the API to return only those students who are marked as female in the database. This is an example of our second proposed solution. Here, the backend is looking for the requested set in a database which stores sets as JSON objects. If a set with the specific parameters is not found, the backend tries to find a source called students and creates the set based on the parameters provided. This set is then stored for faster retrieval in the future. As we can see here, another feature of the API is that it can return sets in a zipped format to be unpacked on the front end side. This is an optional feature which can potentially be useful when the sets involved are very large and transfer speeds are critical.